Questions 21 through 25 on the 2021 Grade 10 AMC 10B. A square piece of paper has side length 1 and vertices A, B, C, D in that order as shown in the figure. The paper is folded so that vertex C meets edge AD at C prime and edge AB at point E. Suppose that C prime D is a third. What is the perimeter of triangle AEC prime? They have told us that this is 1/3, and since this is being folded, although it may not look like in the question, this distance from there to there, if we call it x, will be the same as that distance. So that will also be x. And then this distance here, from here to here, I'm not sure, so I'll just call it z for now. And one thing we do know is that this whole distance is 1, and that was given in the question. So very quickly, we can figure out a Pythagorean relationship in that triangle, since that is a right angle. 1/3 squared plus z squared is equal to x squared. So z is basically x squared minus 1/9, all under the square root sign. X squared minus 1/9 under the square root. But z plus x, we know, is equal to 1. So let's put that in. X squared minus 1/9 plus x is equal to 1. So put that over the other side. X squared minus 1/9 square root. And if you square both sides, you get x squared minus 1/9. And this part would become 1 minus 2x plus x squared. The x squareds cancel from both sides. And all you are left with is just 2x is equal to 1 plus 1/9. That means 2x is equal to 10/9, and therefore x is equal to 5/9. And therefore z, if you plug x back into here, you'll get that z is equal to 4/9. So this is 4/9, and this is 5/9. Okay, so that's pretty decent progress. Okay, so now where do we want to go from here? I need to label a couple things. This part here, from here to here, is going to be 2/3, since this is 1/3 and that full length is 1. And then from here to here, that I don't know, so I'll just call that C. And let's see, what else do I need here? From here to here, I don't know, so I'll call that B. Now again, we've got a Pythagorean relationship that C squared plus 2/3 squared is equal to B squared. And the perimeter that we are in search of is 2/3 plus B plus C, right? It's the perimeter of this triangle AEC prime. So I obviously need to figure out the values of B and C. Okay, I think I can do that. And that will be accomplished by drawing a line from E to this point right there. And then I'll draw another line straight across that makes a right angle with the other side. So this is a right angle right there. And therefore now I can draw it over here just because that's a little small. So let me just draw that same triangle. I'll exaggerate it a little bit like that. So it's the same one. I just wanted to make it a little bit bigger since I have to label it. Okay, so let's label this now. From here to here, that's straightforward. That's just 1. It's the same as the bottom. Now, from there to there, that is going to be C minus 4/9. And you can hopefully deduce that same from the diagram. Now the hypotenuse, that I don't know. So I have to calculate it in terms of my other two legs. So that's just going to be 1 squared plus C minus 4/9 squared under the square root side, right? That'll be basically the value of the hypotenuse. Okay. And then now I can use this triangle right here and a Pythagorean relationship, since that is a right angle right there. So that would give me the following. B squared plus x squared is that hypotenuse squared. So 1 squared plus c minus 4 over 9 squared, like that. Okay, let's see here. Well, b squared is this, so that's really good. I can put that in terms of c, so c squared plus 4 over 9. X, well, x I know the numerical value, so x squared will be 25 over 81, and then that's just 1. So then I can just expand that, c squared minus 8 over 9c plus 16 over 81. All right, so let's collect like terms. The c squareds cancel from both sides. That cancels with that, so that's very good. The 8 over 9c I'll just put on one side, and then everything else is a number. So I've got to get a common denominator and add them all up. So it looks like it's going to be 81 plus 16 minus 36 minus 25. And therefore 8 over 9c is 36 over 81. Solving for c, you get c is equal to a half. Okay, that's a nice number. I can plug it back into here to get b. That's going to be a quarter plus 4 over 9 is b squared. So solving for b, we will get, what, a quarter plus 4 over 9, and then I've got to square it. So that looks like if you had 25 over 36, so that means b is going to be 5 over 6. Yeah. All right, I'm ready for the perimeter. Perimeter will be 2 over 3 plus 5 over 6 plus a half. And when you add those three fractions, you get 2. So, number 21, the answer is A. Ang, Ben, and Jasmine each have 5 blocks, colored red, blue, yellow, white, and green. There are 5 empty boxes. Each of the 3 people randomly and independently of the other 2 people place one of their blocks into each box. The probability that at least one box receives 3 blocks of all the same color is m over n. What is m plus n? We have 5 boxes, 1, 2, 3, 4, and 5. So I can label them. Don't really need to label them, but I will. I just don't want to because it might get a little confusing. But here we go. So the first possible scenario is if all 3 of the same color in box 1. So for example, if we have a situation red, red, and red, like that. Now, that would be one situation. Now, how do we arrange all the others? I've got 4 possible choices for that. I've got 3 possible choices there, 2 possible choices there, 1 possible choice here. So that's obviously 4 factorial. And then the same story for the next person, and the exact same story for the next person. So this is Ang right here. This is Ben over here. And this is Jasmine over here. So 4 factorial, 4 factorial. But that is not the full story. That's part of the full story. We have 4 factorial to the power of 3, it looks like, right? 4 factorial times 4 factorial times 4 factorial. We also have to take into consideration the colors. There's 5 different colors. From that, I chose 1. That is how you figure out the colors. I chose red in this case. But that still isn't the full story because I also have to take into consideration the boxes. From the 5 boxes, I chose one of the boxes. I chose box number 1. So this is the boxes. So this is the full probability. Or not actually probability, but the full number. Probability is obviously most likely going to be a fraction. It almost always is, unless it's 1 or 0. And the denominator is basically the total number of cases. The total number of cases is if this was 5, right? 5, 4, 2, so 5 factorial. But then there's 3 people, so it's 5 factorial times 5 factorial times 5 factorial, so it's 5 factorial to the power of 3. The numerator, of course, is what we are searching for. And the numerator is the big, long calculation. And so far, this is part of that big, long calculation. So we've done the first one. The second scenario is if 2 boxes have the same color. So for example, I had red, red, red. And let's say the second box had, say, blue, blue, blue. Because it says at least 1 box. So it could be 1 or 2 or 3 or 4 or 5. So now, how do I arrange the other? 3, 2, 1, 3, 2, 1, 3, 2, 1. So now let's figure out this one. Now, in a very similar way, it's 3 factorial, but there's 3 people, so to the power of 3. Then for the colors, from 5 colors, this time I chose 2 colors. I chose red and I chose blue. And then from the 5 boxes, I chose 2 of the boxes. I chose box number 1 and box number 2. But here's the thing. Now I've got to add an additional number. Why? Well, this is RRR, BBB, but it could have also been BBB, RRR, with the same 2 boxes, same 2 colors. So as you can see, there's 2 possible ways of doing that. And it's actually 2 factorial. And you'll see that it's something factorial a little bit more clearly in the next example. Okay, we've done 3. Now let's do the next one, 4. Oh, sorry, the next one would be 3 boxes that have the same color. So RRR, BBB, BBB, and then what's the next color? Red, blue, yellow. Yellow is the next color. Okay, so I'll do a yellow, yellow, yellow. So now I think you're getting the hang of it. 2, 1, 2, 1, 2, 1. There's how I placed the next 2 colors. So this is going to be 2 factorial times to the power of 3, right? This is 2 times 1, which is really just 2 factorial. And then now for the colors, from 5 colors, I chose 3 colors, namely red, blue, and yellow. From the 5 boxes, I chose 3 boxes, box 1, box 2, and box 3. And then now, red, blue, and yellow have 6 permutations, which is 3 factorial. And if you don't believe me, I'll just write it here on the side. Red, blue, yellow, red, yellow, blue, blue, red, yellow, blue, yellow, red, or yellow, red, blue, yellow, blue, red. That's 6. And really, it's 3 factorial. Okay, so now I think you have become an expert, so I'll just keep writing the next one. The next one would be 1 factorial to the power of 4. Oh, sorry, to the power of 3. 5 choose 4. 5 choose 4. And this is going to be 4 factorial. And this is when you have 4 boxes that have all the same color. And then the very last one would be all 5 boxes. So 0 factorial here. 5 choose 5. 5 choose 5. And then 5 factorial. Okay, so now what do we do? Do we add them? What do we do? Well, you have to use the principle of inclusion-exclusion. And when you do that, you have to use that, but then subtract that. Use that, and then subtract that, and use that. And when you do that, that will eventually become the numerator. Okay, so let's do this math here. So we've got 4 factorial to the power of 3 times 5 times 5. And then minus 3 factorial to the power of 3, and that's 10 times 10 times 2. Plus 2 factorial to the power of 3, and again that's 10, 10, and 6. And then you are subtracting, let's see here, what's the next one? This guy, right? So that's just minus 5 times 5 times 4 factorial. And then finally the last one is just 120. Okay, so and all of this, I'm just going to do it right now. All of this over our 5 factorial to the power of 3. I might as well. So this is our P. 5 factorial to the power of 3. Okay, so one thing I think I can do is I can eliminate a 5 factorial from each of these. So for example, from this one, if I circled that in one of the 4 factorials, it would make it 5 factorial. So that would be 4 factorial squared times 5. And then from this one, 5 factorial is really 120, so I'm really trying to just eliminate a 120. So from here, 6 times 10 is 60 and 2. So that would be a 120. So it would just leave me with 3 factorial to the power of 2 times 10. Okay, hopefully no mistakes so far. Okay, the next one, again, trying to eliminate a 120, and I think I can do that with a 2, a 10, and a 6. So that would just leave me with 2 factorial to the power of 2 times 10. And the next one, I can combine this and this. That would just leave me with a 5. And then the last one is just 120. And that's all over 5 factorial to the power of 3. Okay, now I can do some number crunching. 4 factorial is what? 24. So 24 times 24 times 5, that's 2880. 3 factorial is 6. 6 times 6 is 36 times 10, 360. And then there's 2 times 2 times 10, so that's 40. That's minus 5. And, ooh, this one here, I had to actually divide through by 120. I forgot to do that. Sorry about that. That would make that just 1. Okay, glad I caught that. And then the denominator was just reduced to just 5 factorial to the power of 2. Okay, so now crunching out these numbers, we get 2556, and it's over 120 times 120. And when you do all the reducing to lowest terms, it becomes 71 over 400. And that is my m over n. They wanted me to figure out m plus n, so that would be 471. It's a very challenging question in my opinion, number 22. That 471 is choice D. A square with side length 8 is colored white except for 4 black isosceles right triangular regions with legs of length 2 in each corner of the square and a black diamond with side length 2 root 2 in the center of the square, as shown in the diagram. A circular coin with diameter 1 is dropped onto the square and lands in a random location where the coin is completely contained within the square. The probability that the coin will cover part of the black region of the square can be written as 1 over 96 times a plus b root 2 plus pi. What is a plus b? The first thing I notice is that they called this a diamond, even though it's technically a square. I think they did that to avoid confusion because this is a square, and if they call that a square, you might get confused. Okay, so let's begin. The first thing, of course, we need to do is figure out the full total region, because the full total region is not the square. And let me explain why. We have this really tiny circle, right? It's a coin. And it's going to be essentially placed all the way around the square, right? So the total region is really just the region that this coin can cover. And if you look at it from the perspective of the centers of each of these will give you an idea of the total region. So first let's label them. There we go. And let's draw lines connecting those centers. When you do, you get this square. And that square is the total region, because the circle cannot go outside the square. So it can't be like this or anything like that. So we can only work in the boundaries of that green square. So what are the dimensions of that? Well, the radius of that tiny coin looks like 1/2, right? Because the diameter is 1. So from here to here is a half, from here to here is a half. So the whole side length was 8. So from 8, you have to subtract 2 times a half, and that is 7. So the dimensions of that square are 7 times 7, which is 49. So that is the total area. Okay, now that we have that out of the way, now let's concentrate on the black areas. The first, of course, is the one in the middle that they have called a diamond for some reason. Let's draw that, and let's draw it. So it's basically a square. So I'm going to draw a square like this. Okay, now we have to figure out how do we figure the region where the coin just touches any part of that black square. Well, I think when it is on the sides, that's pretty straightforward. It's just touching the side like that, and it's always going to be tangent. If it's inside the square, then that's easy, and if it's like that, that's also easy. But we have to look at what is the absolute edge of the boundary, and the edge of the boundary is when the circle is tangent like that. And then, as before, I'm going to look at it from the perspective of the center. Okay. Now, eventually, that circle will get to the edge. It will be like this. And now, the center is here. So, I hope you get the idea. Now, the mistake would be to think, okay, well, the boundary looks like it's all the way around, like that, where that is a half away. And that's partly right, because we have to take into consideration that once it gets to here, it doesn't go there. Let me draw that again. Once it gets to here, it doesn't go like that. It actually goes across like a circle. So let me draw it in. So let me draw in that boundary and illustrate what I'm talking about. So from that point to that point, it will definitely behave like this. And it will behave like that on that side and on this side. Again, in a very straightforward way, like that. But once it gets to those corners, it actually doesn't go straight. It goes like this, like that. A curve. So basically, like as if you were drawing a circle, but a quarter circle. So let me draw in those edges, and now I think we can calculate that region pretty quickly. That region, first the inside square, this guy, that's pretty straightforward because they told me the side length is 2 root 2, right? So 2 root 2 times 2 root 2, that's that square. And then these rectangles, there's 4 of them. So 4, and each of them has lengths 2 root 2 and a half, right? Because this is 2 root 2 and this is a half, because that's the radius of the coin. And then now I've got to figure out these regions. Well, those are quarter circles, and there's 4 of them. 4 quarter circles is 1 full circle. Pi r squared, and the radius is a half. Okay, so that in total, well, 2 root 2 squared is 4 times 2, which is 8. And then this looks like 2 times 2 root 2, 4 root 2. And this looks like pi over 4. Okay, so this takes care of that guy. 8 plus 4 root 2 plus pi over 4. Now we need to concentrate on those rectangular regions. So that one, let's draw in one of those. Now again, we have to figure out how do we do this. Well, the coin cannot be outside, so the coin can be there, and it cannot be higher than that or to the left. And again, I'm going to look at it from the perspective of the center. So the center is approximately there, right? And in the bottom, it would be here, where that center is again, right there. And the maximum it's going to be in this is going to be very small, but that's the maximum it will be, and this will actually continue down like that, and then it will come back up like this. And that will be the region that the coin can just touch or be inside that black region, which is up here, right there. Okay, so now we have to figure out the area of that. Well, I'm going to figure out the area with the altitude. So this is the altitude of that triangle. And the distance from here to here, there to there, that I can easily figure out, because this is, if I remember correctly, 2, and that's 2. So I can easily figure that out. That hypotenuse, I'll call it, is equal to 2 squared plus 2 squared. So 8 squared is equal to 8. So h is 2 root 2. So that means this hypotenuse is 2 root 2. So half of that would be root 2. So this would be root 2. And since this is an isosceles triangle, this is 45 degrees and this is 45 degrees. This is the same as that. So the distance from here to here is root 2. So I'll just call that, well, I'll just call it A. So A is root 2. Now, I don't want that distance. I want this distance, the distance from there to there. Okay? Well, first what I need to do is from that, I need to subtract this little distance right here, right there. So how do I do that? Well, first I need to calculate what it is. And that's a very small triangle, so it's going to be very difficult for me to draw it, so I'll draw it here on the side. This part here is x, that's what I'm going to try to subtract. And then these legs look like they're just a half and a half, right? Because the radius of the circle is a half, so that's a half and that's a half. So 1/2 squared plus 1/2 squared is equal to x squared, so that looks like a quarter and a quarter, which is a half. So that means x is 1 over root 2, and if you rationalize the denominator, that will be root 2 over 2. So to get this distance, first I have to take this distance and subtract from it this little guy. So I have to take a and subtract from it root 2 over 2. And that will give me the distance from there to there. But I want the distance from here to here, so then I have to just add this. And that is the radius of the coin, as you can hopefully see right there, which is a half. So then I add a half. So that's going to be root 2 minus 2 over root 2 over 2 plus a half. And that is root 2 over 2 plus a half. Okay, so that means this altitude is root 2 over 2 plus a half. And then finally, to get the area of a triangle, obviously you know it's 1/2 base times height. But if it's an isosceles triangle, area of, we can use the altitude or the height. And that's just going to be a very nice formula, the height squared. So in this case, the height is root 2 over 2 right here, as you can see, plus a half all squared, so that will be the area. So this is going to be 2 over 4 plus root 2 over 2 plus a quarter, and that looks like root 2 over 2 plus 3 over 4. Okay. But there's 4 of these guys, right? 1, 2, 3, 4. 1, 2, 3, 4. So I have to multiply that whole thing by 4. And when I do, 4 times that, I get 2 root 2 plus 3. Okay, so I've got to take this and I've got to add it to this. So when I do, I get 11 plus 6 root 2 plus pi over 4. And then this is a probability question, right? The probability, right there. So I have to divide by the total region, probability questions. Probability will be basically that total region would be in the denominator, and that total region was 49. Okay. Well, there we go. That's the answer. But of course, they want us to get it in this kind of weird form. And I think it's already in that form, but we have to just simplify it a little bit. Okay, no problem. I think we can multiply top and bottom by 4, and that will help us. So this will be 44 plus 24 root 2 plus pi, and that will make this 196. And I think that's it to get it in that form. 1 over 96 plus a plus b root 2 plus pi. So 1 over 196 plus a plus b root 2 plus pi. So it is indeed in that form. A therefore is 44, b is 24, and finally they want a plus b, so that would be 44 plus 24, and that is 68. 68 for this really nice question. The answer would be C. Arjun and Beth play a game in which they take turns removing one brick or two adjacent bricks from one wall among a set of several walls of bricks with gaps, possibly creating new walls. The walls are one brick tall. For example, a set of walls of sizes 4 and 2 can be changed into any of the following by one move: 3, 2, 2, 1, 2, 4, 4, 1, 2, 2, or 1, 1, 2. Arjun plays first, and the player who removes the last brick wins. For which starting configuration is there a strategy that guarantees a win for Beth? Let's explain this question a little bit. I've got, say, this 4-block wall, right? And then I've got a 2-block wall. And I can either remove 1 or 2. Okay? If I remove, say, this guy, then I have this situation, 3 and 2. Okay, let's see what else I can get. If I remove this middle one, then I have a 2, 1, 2 situation, which is right here. And they're just writing it out as 2, 1, 2. If I remove 2, these two, I get this, which is just 4. And so on. So 4, 1 probably was if you remove just that. 2, 2, I think, is if you remove these two. And then 1, 1, 2 is probably if you removed the middle two. There'd be 1, 1, 2. Okay, so what's our strategy in this question? The strategy is as follows. If we can make a symmetric configuration, then Arjun will win. So let me explain what I mean by that. So let's say we start off with just the answer choices. Why not, right? So I've got a block of 6. It's a 6, 1, 1. So I've got 6, and then I have 1, and then I have 1. So let's make this symmetric, and I'll explain. So I will first remove, we have to just remove either 1 or 2, right? So if I remove the middle 2, because I can remove either 1 or 2, and if I do remove those middle 2, I'll end up with 2, 2, and 1. So 2, 2, 1, 1. That's what I'll end up with. Now, Arjun has already gone. Now it's Beth's turn. Beth, let's say, well, she's got to choose something to remove. So let's say she removes that. Symmetric basically means that you have two numbers that are the same and two numbers that are the same. So, or 4 numbers that are all the same. So this is symmetric. We have 2 numbers that are the same and 2 other numbers that are the same. Because if this situation occurs, then whatever move that Beth makes, Arjun can make the exact same move. So if Beth removes that, Arjun can remove that. If Beth removes those 2, Arjun can remove those 2 and win. So any move that Beth makes, Arjun can make the exact same move and win. Okay, not convinced? Let's try another example. All right, let's say we have gotten to 2, 2, 1, 1. Okay, and I don't want to do this. I want to use something else. So Beth says she decides, okay, I'm just going to remove one of these 2 blocks. So that leaves me with 1, 1, 1, and 2. Well, as I said, Arjun can do the exact same. He can remove one of those blocks. And then that leaves me with 1, 1, 1, 1. So that's what Arjun does. And then Beth removes that, Arjun removes that. Beth removes that, Arjun removes that. He wins because he's the player who removes the last brick. So I hope this is convincing. And if so, we know that A, because it can be made into a symmetric configuration, Arjun will win. So Beth is not going to win. All right, 621. 621 can be made. Well, 621, I will leave that last. Let's do 622, because 621 is the right answer, by the way. But I've got to explain the other ones. 622 can be made into 3131. How? Let's just use this diagram. How I can make that into 3131? Well, you can make it into 3131 by, 622 goes to 2222. And that, I need a new diagram. And that is symmetric if we do the following. If we just remove these middle two, then that would make 2222. So since it's symmetric, Arjun will always win, so that eliminates choice C. And let's do the next one, 631. This is the one that I think I was trying to explain before. Okay, 631, we need a new diagram. So we got 6 here, and then we have 3 here, and then we have 1. This can be made symmetric also. How? By removing these two, you would get 3131. 3131. And as you can see, that's symmetric, right? You have 2 of the same number and 2 of the same number. And this had 2 of the same number, 2 of the same number also. Symmetric. So since that's made into symmetric, Arjun wins there. And then the last one, 632, that can be made into 3232. And you can do that by removing that block. And that would be 3232. 3232, 2 of the same number, 2 of the same number. So that's symmetric. So therefore, E, Arjun wins. So by process of elimination, number 24, the only one where Arjun does not win for sure is B. And therefore that is the correct answer for number 24. Let S be the set of lattice points in the coordinate plane, both of whose coordinates are integers between 1 and 30, inclusive. Exactly 300 points in S lie on or below a line with the equation y equals mx. The possible values of m lie in an interval of length a over b, where a and b are relatively prime positive integers. What is a plus b? On the AMC exams, graph paper is allowed, and so are rulers. So you will take your ruler and graph paper and try to figure out this question. And it's very time consuming, actually. I'm always amazed at how time consuming these questions are, because you have 3 minutes to solve it. So here we go. And here we go. It's a masterpiece, right? So let's explain this. We have all the plots here, all the lattice points, basically. And we have to see if we have exactly 300 points below the line y equals mx. Now, y equals mx, the solid line, we'll talk about the dashed line a little bit later, but let's just look at the solid line. The solid line is the equation y equals mx plus b. Now, since y equals mx plus b, when we draw it, we want 300 points, exactly 300, not 301, not 299, exactly 300. The total number of points, since it's a 30 by 30 grid, the total number of points will be 900. And we want 300, so basically we want a third of them below that line. So that means that most likely this is going to be a situation where m is rise over run. The run is easy, that's just 30. And the rise is going to be from there to there. And if you count those dots, it's 20. So the slope looks like m over 3. So that is what you call the lower bound. And then later we'll figure out the upper bound, but at least this is the lower bound. Now, we have to actually be convinced that this is indeed 300 points. We can't just guess. And the good news is you can do it pretty quickly. You can count the number of dots. So for here, it's 0. The number of dots here is 1, then 2, then 2, then 3, then 4, and then 4, and then 5, and so on. So I'll write them all out. And there you go. And we can add this up pretty quickly. It looks like every 3 we've got a situation where we have one number and then 2 of the next number. So we can easily just say 1 plus 2 plus 3 all the way until 20, because that would take care of these guys here. And then once those are taken care of, we're left with 2, 4, 6, 8, 10, 12, 14, 16, and 18. And we can add those up pretty quickly. So the sum from 1 to 20, well, that's just 20 times 21 divided by 2, and that's 210. And then these ones, you can easily manually add them up. And when you do, that's 90. So 210 plus 90 is indeed 300. So indeed, when we drew the line with m equal to 2/3, we got exactly 300 points below that line. Okay, so we're convinced that the lower bound is correct. Great. Now we need the upper bound. The upper bound is such so that the number still remains 300. So we got the lower bound, but then the upper bound is going to be open, meaning it won't touch it. It'll come close to it, but it won't touch it, because if it touches it, then we're going to end up adding another lattice points, and this will become 301. And we can't do that. We can't have 301. It has to be exactly 300. And that dashed line, I hope you can see it. It's right here. It represents the upper bound. And that upper bound, as you can see, touches this point. And if we included it, it would become one extra lattice point, 301, but we're not going to include it. That's why we're putting a curve here to show that it goes to that point, but it does not include it. Well, since it touches that point, we can easily use that to figure out the slope. The slope is just rise over run, right? Rise over run. And the rise looks like, well, we have to count it. Well, I already did. It's right there, 18. And the run is 28. So that slope, the rise is 18 and the run is 28. But here's the thing. This 18 was only until here. I have to include one more because that upper bound approaches that lattice point. So instead of 18 over 28, it's 19 over 28. And therefore that goes there. Now I know the confusing part is you say, well, if we are including that, then we're including one extra lattice point. So this 300 will become 301, right? How is that valid? Well, because we're not including that point. We're approaching it. And that's what that curve means, that we are not including. We're getting as close as possible to 19 over 28 for the value of m, but not including. All right, so that's about as best as I can explain it. So now we have to figure out the range. And the range is between 19 over 28 and 2/3. So we got to do this math here. And that looks like, if you do that, it's 1 over 84. And that is basically the interval. And it's in the form a over b, right? So this is my interval, range, whatever you want to call it. So a plus b would be just 1 plus 84, and that is 85. For this very challenging and time-consuming question 25, the answer is E.